Okay, so thank you guys for coming for today's session. This will be the last session, talk session for December. So today we have with us Bob himself, and he'll be taking us through everything just from pictures to quantum non-locality. Then we have Harny Wang, who also take us through probabilities from pictures. So welcome again, participants, for today's program, and welcome Bob for to the ELAIS 2024 program, final program. So I'll hand over to Bob to take over his
Hello,
lectures.
everybody. So I'm actually going to do two parts of the lecture today because Anna Pearson, who was supposed to give the lecture today, woke up with a very sore throat, so she can't really do it. And she asked me if I could take over. So I'm using her slides, Anna's slides, so I'm going to start sharing these. Okay, so just a brief recap of where we were already, what we've seen, like from the basics. So you've learned to work with these spiders, and we know they can represent things like states, like when they only have outputs, or tests when they only have inputs. So in general, they have input and output legs. They fuse together. So that's a very simple rule. If you got a bunch of spiders, you can fuse them together. Or if you got a spider, you can also unfuse them. So it doesn't matter in which direction you kind of use them. And then there are some other rules. For example, if you got a spider with two output legs, we just write this as a piece of wire, a cup. If one has two input legs, we write this as a cap, a piece of wire. And if it has an input and an output, we write this as a plain wire. And then you get rules like from your spider fusion that you can just yank a wire, basically, whenever you see it. And if the spiders happen to come with phases, then you can just add these phases up. So this was the stuff we knew about single color spiders. Then we learned some stuff about what happens if you got two colors. You have two colors. And for example, there was this leg chopping, which is if you got two wires between one color and the other color, then they just go away. If you got like a single dot coming into like a fork like that, then it just gets copied. And this is true for both colors. And this doesn't have to be a fork. This can be anything. It just gets copied in all possible directions. So that's something we saw. Then we had this Hadamard gate, of which the matrix is written down here below. And it's self-adjoint, an idempotent thing. So if you multiply it with itself, not idempotent, it's self-adjoint. So it's if you multiply it with itself, with that joint, it just vanishes. And it functions as a color changer of the spiders. So if you decorate the spider on all sides with these color changer, then you end up without those, but the color of the spider has changed. And you can also push it. You can push this gate through any spider to get a spider of a different color. Now, let's go one slide back. So let's look at this rule here on the top left. So what does it allow you to do? What it allows you? Huh?
Hey, what is this again? Who is this? Explain.
So if we look at that rule on the left here, then what it really is doing is it tells you that if you have two cycle, what is a two cycle? A two cycle is like a loop in which there are two nodes. It's like a graph in which there are two nodes. And here we got a green and a red node, and they form a cycle because it's cyclical, so it's a two cycle. And what this rule allows us to do is get rid of two cycles. So whenever you get a cycle with two nodes, well, if they're all the same color, then it just fuses together, right? So that's very easy. If they're of different colors, then these two wires go away. So that's like a way to get rid of two cycles. Now, ultimately, we want to simplify every possible diagram that we get, which we compose with these spiders. As it turns out, with these rules you see here, you will never be able to get rid of four cycles. So what is a four cycle? A four cycle is something you see on the left here. And you see you got four nodes who form a cycle. with alternating colors, because if they would be all the same color, it would just fuse together. If you would have a red one next to a green one, they would just fuse together, and that means that the other two will also then fuse with. So it's only when you got these alternating colors that you actually get something new that we didn't know how to deal with yet. So as it turns out, what you see here is how you can get rid of a 4 cycle. So that's a new kind of rule. And I can tell you in advance that that's the end of it. It's sort of like something I tell you in advance, so it takes away the surprise of the story, but you won't need something like 6 cycle elimination. You won't need something like 8 cycle elimination. Turns out that 4 cycle elimination is all that you need. These are very different things to prove. Actually, Harny Wang, who's speaking the second hour here, he showed what I'm now talking about, that 4 cycles in the end are enough. And I'll make more precise what exactly I mean by all that I'm saying now later. Let's first look at how this 4 cycle elimination works. Okay, so basically the rule you saw before, I present you here a more easy way to look at it. So suppose you got such a 4 cycle. What we're going to do is we're going to enumerate the 4 things which come out of it. So you got like 4 pieces of wire coming out, and we just enumerate them, and for easiness, we use the same color for the nodes as for the numbers on the wires. So you got this green node, which we call 1, the red node, which we call 2, another red node, which we call 3, and another green node, which we call 4. Numbers are unimportant as long as they're different, but we just made them in this color for the following reason. The first thing we do is we completely disconnect these end wires from anything. So you see they're here again, 1, 2, 3, 4, just like they were in this picture. But then instead of having the square here, we get rid of the square. And instead we put like a green dot connected to the red. And what we do then is whatever in the square was connected to red, so the 2 was connected to red, we will now connect to the other color. So now the 2 gets connected to green, and the 3 gets connected to green, while before they were both connected to a red dot. And you do the opposite for the 1 and the 4, they get connected to a red dot, where before they were connected to a green dot. So you end up with this rule. That's how it works. That's how it works. And so the simple way to do it is exactly what I said with these numbers. That's how I do it. There are different ways to write it. You find different ways to write this in math books. But essentially, this is what it does. And now let's look at an example of use. Okay. On the top left here, we got a quantum circuit. This is a quantum circuit. And if you look at it, there's nothing you could do like with leg chopping. There's nowhere you see a connection of 2 wires between different colors. But you don't see anything like that. What you see is squares. You see 2 squares. Here is a square, and there is a square. Can you see my cursor? Can you see my cursor when I move this?
Yeah, it's visible.
Yes,
Okay,
yes,
good.
we can see.
Okay, good.
Yes, we can see.
Yes.
Okay, so here you got a 4 cycle there, or a 4 cycle. It doesn't matter which of the 2 we take. We just pick one of the 4 cycles. Let's take the one on top. I do now exactly what we did before. I put a number 1 on one of these output legs, number 2 on the other one, number 3 on the other one, number 4 on the other one. So here I just enumerated these outputs of these wires. I forget about a square, so I dump the square. I put like a green and a red dot in the middle, which are connected. And then I connect up the green numbers with the red dot, like 1 gets connected to that red dot. Oh, sorry. 4 gets connected to that red dot. So I connect them up. And here, 3 gets connected to that. 4 gets to connect to that. So opposite colors again. And here is exactly what we've been writing. And now you see that I see a green spider connect to a green, a red to a red. So we can connect them. The 2 wires in between go away, and we get a swap. We get just simple swap gate. So these alternating C0 gates, they basically just give us a swap gate. And we really need this square, this rule of getting rid of square to do that. Otherwise, it would be impossible. So, I mean, if you want to look at that, how it looks, to do the same with matrices, you should multiply this matrix with this matrix, with this matrix, and then you pretty much have to guess that this would be equal to this or something like. I mean, you can calculate it, and then you kind of have to guess. Okay, this happens to be the SWOT gate. Of course, in this example, this is still very easy, but once your gates become a lot bigger, this becomes very complicated to do. Now here is I'm going to go to a more interesting example. Like, so what I just explained to you, like this method of let's go to the previous slide. This method to simplify a quantum circuit using these spiders and their rules is in fact the state of the art of simplifying circuits. Like if you go to like Quantinuum compiler or something like that, this is what's happening inside. Sometimes some statistical stuff too, but this is like the best rewriting method that exists to simplify these circuits at the moment. This is the only one that really works. And this is a very simple example. Well, everybody knows this example. Now I'm going to go something a little bit more sophisticated. Suppose you have the thing like here on the top left. So you got two C0 gates, and they can't eliminate each other because there's some phase in the middle. There's some phase in the middle here. Now, how to get rid of that? The thing to realize then is that, man, this doesn't initially look like a square, but in fact it is a square. It is a square in the following sense. It's not a square in the sense that you got these two green nodes and these two red nodes. No, it's a square in the following sense that you can fuse these green nodes together, and then you can pull out this phase. You can unfuse the phase, and you also unfuse this one. And now you see you have a square sitting here in the middle. There's a square sitting there in the middle. Red, green, red, green. We can use the same trick. So this phase is now sitting here. This wire is now sitting there. We essentially get rid of the square again. We stick in the middle a red gate connect with green gate, and then we make the connections like we did this before. And then simplifying, you get this. Now, this is very interesting because initially, in the first picture, we had green dots here and red dots here. So whenever they were blocking any connection with green dots, now you have something which only has two green dots at the side. And as it turns out, you can do this for any kind of configuration like this, turning into something like you see here. There's a lot of science, research papers written about that. And that's like the strategy you can always use to simplify quantum circuits, and which is kind of the best known strategy at the moment. To basically use this trick all the time, you can apply it. So that's an important trick. Now, okay, so we had this, which I introduced as a new rule. Let's look at the time. Okay, I'm doing good. And then we have this one, which we had before. And you can ask yourself how they're related. How are they related? Is there any connection between this one and this one? Well, as it turns out, this one, in the presence of these two copy rules, implies this one. So in the presence of these two copy rules, which are these, it turns out that from this one, you can actually derive this one. But that doesn't mean that you should forget the first one, in fact. Okay, let's see how we can prove that. I think, okay, here is a proof. Let me go to this proof. So suppose that you got this left-hand side here, which is a 2-cycle. I can always turn this 2-cycle into a 4-cycle by simply pulling out nodes like this. So the way you have to think of this is you start here, you fuse the green nodes together, you fuse the red nodes together, and since these are single dots on a wire, they go away, so you get this one. Next thing you do is you actually, now, you can basically use the square popping rule, which is getting rid of this square in the usual way. I didn't draw it out in detail here, but then you end up with this configuration. And essentially, this green dot now gets copied to this red dot. This red dot gets copied to this green dot. And then in the middle, you have just a number that you can forget about without inputs and outputs. So you see from using the square popping and the copying, you can actually derive how you reduce 2-cycle. So this one actually follows from the square popping one and the copying. Now, I already said that you don't need anything more than getting rid of squares. It turns out you don't need anything more. There is one more rule you need to what we call have a complete system. A complete system means that every equation you can derive using vectors and linear maps and in Hilbert space, you can derive with these picture rewrites we've been teaching you. So there's nothing more you can do using linear maps and stuff like that as far as deriving equations is concerned than you can do with this picture. It turns out you need one more rule for that, but that's actually one you never use in practice. So wait, where is it? Okay, here it is. Here it is. So the rule is that if you got like on a single line, something red and something green and something red on a single line, you can always swap this to something green and something red and something green. If you look at the picture on top, there is nothing you can do here. You don't really have a square here because you got 1, 2, 3, 4, 5, 6 nodes alternating. So there's nothing really you can do. However, if we use the ones on the bottom, like Anna has done here, look, here there's nothing you can do, but by changing red to green, red, green, you can fuse the green ones, and you really get again a square, just like we do before. You get again a square, and you can get rid of it. So that's why actually in the end, oh, sorry, that's nothing. Squares actually are enough. Squares are enough. So that's really everything we need to say, I think, in this particular lecture. So Anna wrote down some conclusions. I'll tell them. So basically, big and ugly, I mean, these are things you knew already. Big and ugly difficult matrices can be obtained using spiders only. Spiders and their rules can be used to make cheap quantum circuits, and this saves time and money for those who build use quantum computers. Now, the main point to take is that if you go to the first slide here, everything just from spiders, everything just from pictures, you actually need to take this literally, that any equation you can derive using matrices and all that, you can derive using pictures. So that's the bottom line here. Okay, so now I want to explain what I was going to explain today, and we will need this here, which is quantum non-locality. So I'm leaving these slides, and I'm going to give a much, so rather than just giving the lecture, I thought I give a much broader overview from the entire story of what we've been talking about. So it goes a little bit away from what's in the book, but I think at this point it's important to sort of get a more broader picture of what you've actually been learning. Is everybody still with me? Everything is okay? Everybody can see the slides?
Yes.
Yeah.
Oh, perfect.
Yes, please.
Okay. So this is going to be a little bit of a detour. That's why I wanted to spend a bit less time on the first part. So we're going to talk about the language of quantum. The language of quantum is due to John von Neumann. I mean, you probably know John von Neumann for quite a few things, or you may know John von Neumann for quite a few things, because the computer architecture, like we use it now, is due to John von Neumann. The field of game theory, which is used a lot in economy, is due to John von Neumann, and many other things are due to John von Neumann. Now, what is also due to John von Neumann is the use of Hilbert space and linear algebra for quantum mechanics. Use of density matrices, if you know about that, that's all due to John von Neumann. Now, something very remarkable that John von Neumann once said was he publicized the Hilbert space formalism for quantum mechanics in 1932, and in 1935, only 3 years later, that he publicized the Hilbert space formalism in his book, Mathematische Grundlagen der Quantenmechanik. This is in German. He said, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So he denounced, John von Neumann denounced his own Hilbert space formalism 3 years after publicizing his book about it. I'm not going to go into details of why, because this is today actually less relevant, But the bottom line is John von Neumann himself, the father of the Hilbert space formalism, didn't believe in it himself anymore. And he spent a lot of time looking for other languages for quantum. I call these languages for quantum. Okay, so now one thing that was really important for John von Neumann about quantum mechanics was the concept of measurement. He felt that measurement in quantum mechanics or observation in quantum mechanics is the most important ingredient of quantum mechanics. And a lot of people still think that today that measurement is the most mysterious ingredient of quantum mechanics. So and especially the fact like that measurements disturb the quantum system. That's what measurements do. If you try to measure, you disturb the quantum system, and that's a little bit the same as like this little girl who comes in a dark room, wants to know where the balloon is, and the moment all she can pretty much do is kick the balloon because she can't see where it is, so the balloon will be away again. So and that's a little bit the same with quantum systems. You give them a kick when you measure them. Of course, it's a bit more subtle than that, and that we will learn about that today when we talk about non-locality. So let's start with Schrödinger, which you may know from his equation, Schrödinger equation of quantum mechanics, or from his cat, which was like a conceptual, if you may, paradox, or it's not about the nature of quantum measurement in particular. So he was actually, his cat was about really the phenomenon of quantum measurement, like and maybe the problem with it. Now, unlike von Neumann, Schrödinger didn't think that the measurement was the most mysterious ingredient of quantum mechanics. He didn't thought that, despite the fact that he's known for his Schrödinger's cat. So in this particular paper, also from 1935, which is the year when John von Neumann denounced the quantum mechanical formalism, he wrote, when two systems enter into temporary physical interaction, which essentially means that you just got two systems. You just got two systems. That's what it means. Then stuff happens. And Schrödinger says, I would not call that one, but rather the characteristic trait of quantum mechanics. So he believes that the most important thing in quantum mechanics to understand is not measurement, but composition of systems. That's Schrödinger's idea. And I'm going to give again a little metaphor, just like I did with the little girl and the balloon. So if you think about a concept of twins, so having two people, then when I say okay, consider twins, you know nothing about these people. You don't know nothing, no property about one or the other. The only thing you know is that whatever property one has, maybe the hair color or the eye color or whatever, the other one will have exactly the same property. They will be equally tall, they will be, so whatever property one has, the other one has, but the concept of a twin itself gives you nothing. And that's a little bit like maximally entangled state in quantum mechanics. You know nothing about what you will get in a measurement of one system, but you know that whatever you get in one, if you do the same measurement on the other, then you will come the same. Now, quantum non-locality, which we are going to see later, is about the fact that if you got two systems in quantum mechanics, you cannot explain them anymore like we explain twins. You cannot explain them anymore. And whenever measurements are involved. So the two concepts come a little bit together, like measurement and entanglement come together in the notion of quantum non-locality, but I'll talk about that later. Okay, so this is Roger Penrose, is here in Oxford. I'm based in Oxford, and Roger is here in the mathematics department. So people know Roger Penrose from Nobel Prize and black holes, of course. You may know the fact, if you know Escher, the painter Escher, that a lot of the ideas which Escher painted came from Roger Penrose, in fact, from mathematical ideas from Roger Penrose, because they happen to be friends. Now, something else Roger Penrose is known for, and this is a picture from a paper in 1970 or 71, I don't know, but Roger Penrose was doing this, what you see here, already probably in the late 50s, early 60s, when he was an undergraduate student. He didn't like the typical notation people use in relativity. He didn't like that. So if you have a tensor here, Q, A, B, C, superscript, FG, subscript, then he preferred to write them as blobs with wires coming in and wires going out. Of course, you immediately recognize what we have been doing in this course, like representing linear maps and all that by tensors, higher tensors, by blobs with like input wires and output wires. So Penrose was doing this for a long time already, like, and started this as an undergraduate student because he liked to study, in this case, general relativity and stuff like that, better with these kind of pictures. Okay. Right. So let's summarize a little bit. Von Neumann wanted the new quantum formalism. And I said he wanted the new quantum formalism. Schrödinger said that quantum is about composing stuff. That the most important thing in quantum is how you compose stuff. So
hey,
we need.
Good night, then.
Yes, the most important concept is composing stuff. So maybe if we want a new quantum language or quantum formalism, we want to start from composing stuff in the first place. And then Penrose uses pictures instead of symbols to represent things in physics. So as it turns out, making your theory about composing or using pictures instead of symbols is pretty much the same idea. It's very much the same idea. And everything we've been teaching you using these pictures is very much like reasoning about physics in terms of composing stuff. In terms of composing stuff. Okay, so what you've been learning here is really the incarnation of getting quantum mechanics for, in terms of what Schrödinger thought is the most important, composition of stuff, and what also Penrose liked as a language, which was using pictures, and it corresponds to the same thing, basically. So I thought I wanted to give you this historical context to see where this came from. It's not that suddenly we thought, okay, we want to turn quantum mechanics into pictures. It was more thinking about the notion of composition in quantum mechanics like Schrödinger that we ended up accidentally with pictures and then realizing, okay, by the way, that's what Penrose had in mind too a long time ago. So that's how we ended up doing this quantum theory in pictures, which now, of course, is practically used a lot in quantum computing. I don't know if everybody told you about that, but we did an experiment. We wanted to show that indeed this is much simpler to do than using Hilbert space. So we did the previous, not this summer, but the previous summer, we did an experiment. And then there was this full page in The Guardian specifically about our results. Yeah, the picture you see here is where I'm sitting now, by the way. At home in my music studio. So what did we do? I don't know whether, so what did we do? We basically took the book and then we have video lectures, which we soon will publicize too, of the entire book. So we made lectures of the entire books in my office, not like here, not to people, but just video lecture in my office, like and then we also have exercises, and as far as I understand, the exercise we made will soon be distributed to you, if you want them, together with the solutions. So we had a full course. We had lecture notes, like the book. We had the lectures, filmed lectures, not live lectures like here, but filmed lectures, and then exercises with solutions. And we took like 8 weeks, just like we did here in this course. We did exactly the same thing. We spread this around 8 weeks, and then we did a call in the UK to high school students, and we asked them who wants a free course this summer. So, and then we were going to basically give them the teaching materials. We're going to ask them to try the exercises, to watch the lectures. What we were doing essentially was giving a course exactly like courses are given at Oxford University as postgraduate level. At postgraduate level, that's how courses are given, although they're typically with live lectures in person rather than video lectures, but otherwise they were exactly the same. Logistically, it was just impossible for us to work with live lectures, which of course is a disadvantage if you can't do that. Anyway, what we did next, okay, I'm going to go to the next slide. Oh, no, I'm going to wait. What we did next is we asked them to do an exam, but the exam entirely consisted of questions of Oxford University postgraduate exams. So postgraduate, like people who are doing masters and PhD courses, we took exam questions for that, and we asked them to the students which were typically between 16 and 18-year-old. So they were high school students, between 15 and 18, something like that. So we asked them to do this exam. We did tell them that it doesn't matter. However you do, we're going to give you a certificate that you actually took the course. We're going to give you a certificate anyway, but please try. And so as a result, 50% of these high school kids after this course got a distinction on Oxford University postgraduate exam. And of course, that proves that not only this way of formalizing things is very useful to do in the for quantum computing and all that, because there's a lot of applications now in quantum industry with big companies using it a lot. But it's also a much easier way to teach people quantum at a much earlier stage without any necessary mathematical background. And I think so when this course started, I sent the recorded introduction, and I think in particular in countries which don't have the traditional Western way of having science taught at school may have advantages here. So that's my belief, that if you go away from the Western scientific world, that you may actually have advantages with this way of thinking. Because one of the results we saw, I don't know whether I've got a slide here. I don't think it's not on this slide, but we saw that the 15-year-olds did better than the 18-year-olds. Why is this the case? Because the 15-year-olds have less to unlearn. They have less sort of typical Western scientific thinking, which is very reductionist, which is very sort of static. They have less of that, and therefore they're much more familiar. So some of the results which we saw is, so basically left on this graph, you see that very few knew anything about quantum when they started the course. What is another beautiful result is this table. The majority of people say that the course strengthened my motivation and confidence and motivated me to pursue a STEM career, like a big majority said that. It didn't depend which schools, because in the UK, there's different school systems. You got private schools, state schools. There was really no difference in the marks between the different schools, which is a nice thing to see. And the amount of time the students spent wasn't much. Like spent per week for these 8 weeks was typically like between 1 and 4. So which is not much at all. Anyway, so this is why we felt that it's a good thing to now start teaching this course and bring these materials available outside of the UK, especially after this experiment, that is a way that many people in the world can actually learn about quantum. And so we have several projects going on. And for example, you see KNUST here at the bottom is one of the projects we have going on. So there's more than this now on trying to basically bring this way of thinking quantum around the world. And I mean, this was not a little effort. There's lots and lots of people were involved in actually making that experiment work, having all the materials produced, and these sort of engagements which we are doing. Like the people who have been involved here, that Katerina did so much work for bringing this course to Ghana, and other people like did a lot of work too. So thank you all to them. Okay, quantum non-locality. So let's now try to explain quantum non-locality, which is considered as the most unpenetrable feature of quantum mechanics entirely in this language of pictures. I mean, when you read about this, typically in books, there is a lot of words. People have to make an argument which involves a lot of words, and we're going to try to avoid the use of any words. Of course, I'm going to use words to explain the pictures, but in principle, you don't need these. In principle, you don't even need these. So what is quantum non-locality about? You remember these two pictures of the twins. And so why are these twins the way they are? That whatever property one has, the other one has, is because, of course, they share their genetic information. They come from the same genetic material, and therefore the same properties, physical properties, manifest themselves in both parties of the twins, right? So the thing is, in quantum mechanics, there are also things like twins, two systems far apart, and whenever you measure one, then there is some direct relationship with whatever you measure from the other. But what quantum non-locality means is that you can't explain it in any way, like, for example, coming from genetic material in the past, from some common source in the past. You can't explain it like that. That's quantum non-locality. You can't explain occurrences far apart, which clearly are strongly correlated in a way from there being some common cause. That's the terminology. From there being some common cause in the past, like, for example, in this case, the genetic material, which determines how the twins look. So we're going to show that something like that is impossible in quantum mechanics. We're going to look at the following type of configuration. You got some state in the past, which is this white triangle. That's some state in the past. And then you got three parties, A, B, and C, and they each can do stuff to one of three states which come. So basically, this triangle is a three-stage system. You got three states. They were together in the past. You send them to three different places, and in these three different places, people can do things with it, which typically will be measuring it. They're going to measure it, and as we go see, quantum mechanics will then predict something about the connections between these measurements. And then we will compare this to what would happen if, like in the previous picture, there would be some common source that determines everything in the past. Okay, so this is really one of the most sophisticated things you can explain in quantum mechanics, but so that's why we kept this to the end. So really, So really what A, B, and C are going to do, they're going to do each a measurement, and what in the usual language is called an X or a Y measurement. I mean, these are not exactly the green and red ones, but think of them as green and red ones. The Y isn't really like, so the green, the X measurement is a red measurement, the Y measurement is actually a rotated X measurement. And you will see how we do it. It's a rotated X measurement, but you can think of it as two kinds of spiders if you want it for real, but it's not that important. Okay, so, and what we're going to do is, so we got A, B, and C, and they are allowed to choose whether they want to do X or Y. They are allowed to choose whether they want to X or Y, and they do this independently. And they can be very far apart, like these three boxes can be, like, say, on different planets or even on different galaxies if you want. They can be very far apart in principle. And it suffices for the argument to look at four possible configurations of choices made by these three parties. So they each are going to make choices, and we're going to look at four possible configurations. And then we're going to look at all these results together. We'll pick all these results together, and we're going to look at a property. This will actually be, like I said, it's like the parity, the overall parity of the different outcomes you get. So that's the sort of thing we will be looking at. We will be looking at this situation in quantum, and we will be looking at that situation if there would be some common genetic material. I mean, I'm going to keep using this type of metaphor of common genetic material like the twins have. Okay, so this is the quantum situation we will be looking at. So we got these four cases, and so when you see X on the previous slide here, this actually means like doing this red dot with nothing, which actually means doing nothing. A red dot with nothing, it means doing nothing, and then you do a green measurement. So in the first case, you 3 times you do like literally nothing in the red dot, and then a measurement in the green variable. Okay, so that's really that's an X measurement. Now so you got this green, and then the second case, on the first one you do nothing, and in the other ones you first do it 90-degree rotation, and that gives you the other measurement. Here you got one rotation and another rotation, and one rotation and another rotation there. So there are 4 different scenarios. There are 4 different scenarios here with particular choices of measurement, and then you basically bring them all together and you do something. And what you do is just a red dot, which actually, as it turns out, as we saw in the classical sort of chapter, means doing a parity measurement. You measure the overall parity of what you see in these 4 situations. What we're going to do now is calculate them. So you have these 4 different things. You have these 4 different things here. So again, this is A, B, C. Like I said before, this is A, B, C. And This is the parity measure. I'm just repeating a lot. Now, so basically what we want to calculate are now these 4 different things here. Now you see that these red dots can all fuse together. These red dots can all fuse together. They will all fuse together. You have to be careful a bit because they're double dots. They're double dots, but they can just all fuse together. Next, you actually use square popping to show that I'm not going to do this explicitly for the sake of time. You can use square popping then that you actually get the following 3 results. So this one is equal to this one is equal to this, and this one is equal to this, and this one is equal to this, and you use square popping for that. It's a little exercise. You find it in a book. It's quite a straightforward calculation. I don't want to do it here because this would deviate us from the argument, and the argument is already complicated enough. So going back again, we had these 4 quantum scenarios. Here, we have these 4 quantum scenarios here at the bottom. We compute, we get these ones. So all together, what do we get? I'm substituting them here. Can now fuse everything together, and all together you get 180. All together you get 180. This is all going to fuse together to 180. Boom, 180. So that's what quantum mechanics tell you, that you get in this situation. So to repeat, we have a situation where we have 3 parties, all the way back. We have 3 parties. They each get a quantum system, and then they do something to it. And they can choose what they do to it. We consider 4 possible situations, and then we compute something about what they observe, what each of them observe, and the result is this, which really is the number 1. We've seen that, which really is the number 1. That's what we get. All right. Okay. Now we're going to see, I'm going to go back, the analog of this. We're going to look at the analog of this in this situation, that there are some common, think of it, genetic materials. This can be probabilistic, no problem. This can be probabilistic. I won't go into details there, but this can be probabilistic, which determines what these people here observe in their measurements. Suppose this is the case. So I'm going to go further. That's here. That's really here. So we have 3 measurements. I call them X and Y. And this is X and this is Y. These are the 3 possible measurements everybody can do. And you see them here at the bottom, represented by the 6 boxes, is what would be encoded in the genetic material as an outcome for these measurements. And now it looks a bit messy, but like the first measurement, remember this one was doing nothing, and this occurred here in this one on the first place, and yeah, that was it in these 2. Let's go look again. Yeah, here. So doing nothing on the first one occurs in this scenario and in this scenario. So in the first 2, doing nothing on the second occurs in the first and the third, and doing nothing on the third occurs in the first and the fourth. And we're going to see we're going to do exactly the same here. So doing nothing. Okay, so I'll have to go this on the first or the second. Doing nothing here on the first and then if you follow carefully on the third, doing nothing here on the first and on the fourth. So that's exactly the 4 scenarios we see. And then the ones with the star is actually doing something. And then these are just the alternatives. And you could go through it. It's like a bit of a spaghetti. It's a bit of a spaghetti here, but it's exactly the way one should think if there is some genetic material in the past that actually determines what observations we see in the measurement. That is literally what you get. And the reason this is all chosen like that with these 4 different systems here, who each have like some possibilities. The reason is basically to get to the result we will see now. So okay, let's compute it. So again, we got this 3 system A, B, C. I'm repeating it again. They each inform the possibilities of the 4 scenarios we consider, and now we're going to start calculating. Okay, so these are really these numbers are. Oh, sorry, this should be 180. These numbers are talking about. Now, look, we have a green dot here because the green dot is just copying copying that information to the two possibilities. That's what these green dots are doing. They're just copying this data. This is classical data. It's all single. It's all classical data. So just copy it to the relevant path. But you see, there's always two wires between the red and the green dot. So they vanish. They vanish. And so the result is really a red dot without a number in, which is the number 0. So in the case where there are things in the past, in the common past, which determine your observations in the future, for the same scenario, in the classical case, you get 0, and in the quantum case, you get 1. 0 actually means even, and 1 actually means odd in terms of parity. So necessarily even parity, if there is like classically, if there's some sort of common cause, odd parity, if you follow the rules of quantum mechanics. So that's a contradiction. That's a contradiction because 0 is not equal to 1. Okay, what's in the 90? Sorry, that's a typo. This 90 should be under the 80. Sorry about that. But this is contradiction. This is contradiction. And that's why quantum mechanics cannot be explained in the way we would explain twins and their common relationships. So that's basically the proof of quantum non-locality in a simple way. So all our resources, also from all the experiments we have done here at Oxford and things we have filmed, and they will be made available. From what I understand, is that the exercises, which you see on the bottom right here, will be made available to you too. And also, I think the exams, which we asked the students to do, will be made available. If you want to have a go at them, I do strongly recommend to first try to do the exercises, because it's very hard to just read a book and then expect that you do an exam without doing some exercises. So there will be the recordings, or these recordings which we're giving you. We cover the same material. Actually, here we covered more material, because I don't think that in the course initially we did quantum non-locality, for example. But so these materials will be made available. So that's the end for me. Since there will be another lecture after this, I suggest that if there are any questions, that we can do this now, because this is not an easy concept which I try to explain. So there's thousands of books written about that. It's not an easy concept at all, and it's not completely understood yet, as far as I'm concerned. We haven't completely understood this yet. What we have are these kinds of proofs that you can't explain things with a common cause. And this actually has practical applications. This actually has practical applications because it allows you to detect if you're trying to do some quantum protocol communication or something like that, whether somebody has been messing around with it. You can use basically this sort of arguments to check whether your information is still purely quantum and hasn't been intercepted by a measurement or something like that. Because then the argument so basically the fact that you can't explain this classically is a way to protect your information by then checking that indeed it satisfies these quantum correlations, which can't be explained classically. Okay, I see there are some things in the chat. Can I open the chat? Sure, you can have the slides. I'll need to correct this one typo which I just observed because it shouldn't be there. I don't know how familiar you are with the lectures of the Royal Institution, which is an old historical organization based in London. But I think very soon I gave an extended version of this particular lecture, and it will be put online and made available there. So there's some more details there, the Royal Institution from London. But yeah, I'm perfectly happy, of course, to make the slides available here. Well, it depends on, the question is, does it mean that identical twins are not quantum entangled or are not like quantum entanglement? It's a good analogy, of course, to think about it, but you can't explain them. You can't explain quantum mechanics. Sometimes you can, depends what you're going to do. But in general, you can't explain quantum entanglement by thinking they have some common, there is some common source of, say, information of data available. So what people then tend to interpret is that something happens instantaneously. Something happens instantaneously between these different parties. However, it's not something you can use to signal information. Otherwise, you would be violating relativity theory. But it seems that it cannot be explained from all coming from a common past. It cannot. And at the same time, you can't use it to signal information, but you can study your correlations to see whether they are generally quantum correlations. And this, like I was just explaining before, can be used to verify that if you try to do some establishing some correlations or something like that, then you can basically verify this using effectively the fact whether these are still genuine quantum correlations and not something you can classically produce. So a typical example is one way to check in quantum key exchange, whether you're working with proper entangled states is to verify what people, and these typically are only two systems, and then you verify what people call Bell inequalities. So if you hear about Bell inequalities are statistical inequalities, but they do essentially the same thing as I've been trying to explain today. There's still statistical inequalities which check that there cannot be a classical causal explanation from what you observe. So Bell inequalities are statistical. It's about one number being bigger than something. So what I showed today is not a statistical argument. It's like a logical argument. But for that logical argument, you need three systems. You can't do it with two. So the logical argument is due to, the particular state is called the G8C state, which stands for Greenberg, Horn, and Zeilinger. And so Zeilinger is the one who got the Nobel Prize specifically for showing this thing which I've been explaining today in the lab experimentally. Of course, he also showed teleportation for the first time, but he also showed experimentally in the lab what I was explaining earlier, and he used photons. He used photons for that.
Hi everyone, I'm Harny. Today I will give the last lecture for this course. So which is probabilities from pictures. As we know, any ordinary book on quantum theory will talk about probabilities, right? In this course, we haven't really mentioned it. Is there any? So now it's time. I think now it's time to deal with this kind of probabilities. So what is because this course is about the pictures for quantum theory. So what is probabilities looks like in this picture formalism? So basically, the idea is very simple because any probability they are kind of number, right? So the problem becomes, how do we represent a number by diagrams? And the answer is very simple. So numbers, they are just diagrams with no inputs and own outputs, like this diagram. You can see there's no outputs, there's no inputs, it's like that. But this is a general box. So we can give some examples. So like this, the green node, this green node is a phase 0 spider, special spider. Here you can see there's no legs, right? So no input, no output. Also this one, you can see there's green one, phase 3, and there is 180 degree phase, which is red. They're connected, but still the whole diagram has no input, no output. Similar here, there are 3 phases, right? Although the middle of them, this part, there has input and output, but the whole diagram has no input, right? And no output. So it still represents a number. Similar here, so there's a phase. You have on this side you have input and output, but here they are connected. So in total, there's no input and output. And this box with the discarding still has no input and no output. So these are all concrete examples of diagrams which represent numbers. So you can see the idea is very simple now. To represent a number, you just need to use diagram with no input and or no output. But particularly for probabilities, they are kind of special, right? So how is the diagrams looks like for probabilities? So here we have some very simple math for the probabilities. So first we have some very special number which is represented by some special diagrams. First is an empty diagram. So we use the dashed square to represent it, but actually it's an empty diagram. It's everything, the nothing there. So it's an empty diagram. The empty diagram is a special, represent a special value, which is just one, the unit, the number one. And a single red circle or green circle, they represent the number 2, and which has no these two spiders, they have no face, right, or face 0. But if the green face with no input no output, but the degree is 108, and then it just represents the number 0. So these diagrams represent very special numbers. We will use frequently in this lecture. And also, actually, any state X. So if we discard its output, then as we said, there's no input no output, then we'll get a number. Actually, this number is the probability. Obtaining these states. So we will get a probability. Especially, we learned about short state before, right? So short state is a state which has probability 1. So that means you will definitely have this state. So that's why if we discard the output, that's why it's called short state. Okay, so if we have 2 diagrams which represent 2 numbers, and we put them in parallel, then we will get actually the multiplication of these 2 numbers. So if we have a diagram represent X, another diagram represent Y, the number Y, then we'll get X times Y. So it's easy, right? So you just put them in parallel. If we put them in parallel, then they're just the diagram represent the multiplication of these 2 numbers. For example, so as we have said, this green circle, phase 3, represent the number 2. So if we put 2 green circles together, then you will get 2 times 2, which is 4. So if you put 3 circles together, then you will get number 8, right? But if you put the 108 degree green circle with the 0 degree green circle, so then this is 0, as we have said, this is 0 here, and this 2. So 0 times 2 is still 0. And also, if you have 2 empty squares, is still empty diagram. So each of them represent 1. So 1 times 1 is still 1. So you can see if you have diagrams which represent a number, then you can then you can freely move them around. You won't. It still represent a number. It won't change anything. Okay, that's a simple mathematics of the diagram for numbers. Okay, so now we have the diagrammatic representation of numbers, especially for probabilities. So with this, we can revisit what we have encountered before in this course. First, we can look at the quantum cap and cap again. So we have said before that quantum caps like this, you have double Y, right? The cap. So actually, we said they are short states, but they are not really short because we just defined that short states means if you discard outputs, you will get you will get number 1, right? But if now we discard the quantum cap, so which means, okay, discard means you have a single cap on top. Then they just they're all connected, right? So become a circle. So as we said, a circle, a cap. This is a single cap, and a cap. They are special green, right? Green cap and special green spider, right? So it become green spider, which phase is 0. So as we said, this is 2. So it's not 1. So this is not, by definition, is not the short state, the quantum cap, but it's very easy to fix this problem. So we just need to multiply with a number with this quantum cap. We put the inverse of the green circle, which is 1 over the circle, which is just 1 over 2. So why do we do that? Because if we put half 1 over 2, put this half with this quantum cap and discard it, and then we can see that this one, as we already seen, this one is just the green circle is 2, right? So you got this one, and you put them together, they just means, okay, you multiply them, and then you got half times 2, you just get a 1, right? So okay, so now so that means, okay, with this number, if you do the discarding, then it's just 1, you get number 1. So it's perfect short state. So that's the way. So how do you get the perfect state, the short state? Okay, similarly, you can do a similar thing for the quantum cap. This is a quantum cap, but now it's quantum cap. So if you put the same number, which is a half, it's a 1 over green circle, you will get the short map for this quantum cap. So that's the way. Once we have the diagram representing a number, then we can use them to fix something we didn't really mention before. Okay. Furthermore, so if we look at the quantum interpretation, we also didn't do the calculation of probabilities before, right? So if now we want to teleport a short state, which we do like this, and then we want to discard it. We want to see the probability that the cap test will happens, right? Okay, so to see the probability, we just need, as we said, we just need to discuss the output. Because now the test and the quantum cap state, as we said, is fixed by a number. So we need to put this number here and here. So because this is a cap, this is a cap, the quantum cap. So we need to put these two numbers here, and then because of the yanking rule, we get this one, right? And also, as we said, you can freely move the numbers, that the diagram for numbers, that put them together. Okay, so now, as we said, by definition, this is a show state. So which means if you discard the output, you will get number 1, right? So we get a 1 here, and we have a 2 half here. So which is half and a half times together, you got 1/4. That means the probability. That means this probability is a quarter, it's 1/4, right? So that's the way. Once now we have this diagram for numbers, we can accurately to calculate the probability. Okay, that's for the quantum interpretation. So do you have any questions? Okay. Okay, let's look at the let's revisit the quantum gate computing, right? So as we know, the quantum gate computing is about in this calculus, in diagrams, is about how to use the diagrammatic equality, right? To do rewriting, to change the diagram, and then we get the final get simplification. But to do this, we need to check. So we need to check. So that actually, because before we ignore all the numbers, now we want to check whether the rules we have before is exactly strictly equal. So for example, a very typical rule is called the copy rule. So like a green quantum state, this quantum state can be copied by a red spider. But we want to check whether this is strictly equal. So we do discarding on both sides, left and right. So on the left, you can see we can see if we do the discarding and two outputs, then that means, okay, discarding just means we put a single cap here, right? Here is also discarding, we have a single cap here, right? Okay, so now we want to calculate, simplify this diagram. So, and then we write them into a single diagram. So what does this mean? This means, okay, it just put the green, this double green circle just means two single green circle, right? So this similar, this red just means two single red, and they're connected separately. But here, so the connection is okay. So this red connect to this red, and again this red connect to this red again. So now because of the fusion, right? The spider, we said the spider with the same color, they can fuse together if they are connected. So now you can see this one, this red spider is connected with this one, right? With two Ys. But no matter how many Ys, once they are connected with the same color, so they fused together, right? They fused together. And keep the connection, right, to the other nodes, like here, they keep the connection, right? They are now here that this part just fused together. So you get this. And also we said if this is what is this? This is a cap, right? It's a cap with a red circle, and degree is 0. So it's just, so this is equal to the cap, right? This is I think we mentioned this before. We learned this before. So these two green connected. They are connected, and you can fuse them again. So you get this one, right? You get this one. As we said, this single green circle is just the number 2. So basically, once we discard the output, we will get number 2. Okay, now let's check the other side. The other side is this one. So if we discard here and here, then similarly that means, okay, this discarding just means, okay, this, a single cap here and a single cap here, and similarly we write the double diagonal into a single. So that means, okay, this one becomes this one becomes this. They are connected, and then you fuse them again, you get a single circle, green circle, and a single green circle here. So this circle represents the number 2, and this also number 2. You put them together, means multiplication. So you got 2 times 2 equal to 4. So, okay, so that means now, these two. So these two, if we do discarding on this on both sides, we didn't get the same number. On the left we get 2, on the right we get 4. So they're not strictly equal. So how to fix it? Because if they're strictly equal, that means if we plug the same thing, you will get this. You will get the same number. So, how do we fix it? The idea is the same as we did before, right? So we just modified with the number. So here we get 2, and here we get 4. That means we want to multiply 2 here, right? Multiply 2 here. So so that means we need how to say, we need to let this one, and we need to let this one, this side, to the number to become smaller. So so that means if we do the so we want to make we want to have a show state for this. That means if the discarding of this, the probability of this one is 1, then this also 1, then you will get the same, right? So how do we get the show state of this one? So we do discarding. So because here, so this one, the same thing, the times itself, you got 4. So that means, okay, the single diagram is equal to 2, right? Equal to 2. This equal to 2, that means, okay, if I times the inverse of this, that means I times half, then I will get 1. I will get this thing will become 1, right? So that means okay, this diagram, that means this diagram is a short state. It's short state. So so to make this thing strictly equal, so we just need to add them, to add this circle, because this is 2, this is 2, this is 4. We just need to add this circle here, the green circle here, and then you can see, if you do the discarding, here you will get 2, right? This number won't affect anything. So you do the discarding, as we said, this you get 2 times 2 equal to this one. This do the discarding, you get 4, right? So you will get the same scalar, same number. Okay, so and that means okay, we can modify this one with a number, adding this number, and then we get this strict equality. Equivalently, if you move this to this side, this from left to the right hand side, and then that means okay, here you will get a half, right? 1 over the green circle, you will get this. So these are clearly equivalent, right? So similarly, if this the other copy rule, so here is copy the green, and copy the green by the red. Here you copy the red by the green. It's very easy to check; they are the same. They're quite similar. So you also, to make them strictly equal, you need to add this green circle, or equivalently on the right side, you can add this half here. So now this we find a way to how to fix this problem, the copy rule, which we have used a lot. At the same time, if we another conjugate, there's a conjugate called C0 gate, control NOT gate, also need to be checked, because if we look at the definition of the C0 gate, that means you before we draw like this, just this part, right? But by the definition of the C0 gate, if you input 0, 0, you input 0, 0, you will get exactly 0, 0, right? You will get exactly 0, 0. So let's check whether if we add this, whether we get exactly the 0, 0 state. So now, if we input these two scalars, sorry, the red state, the red state to red state, and then as we said, we need so we need to make it how to say, if we put 2, 0, 0 to red state, we want to get exactly the red state, right? So if once we do input them from the bottom, plug them from the bottom, then you can see we can do the fusion rule first. Here we can do the fusion rule first, then it becomes here, and then because this is a phase, the degree is 0, so this just become a plane line, right? Just become a plane line, and then again this part. As we said, for the copy, you need to be strictly equal. You need a green. So here, together with this green, you get this two. You get this two. So that's so that means, okay, we for the C naught, if you want to if we want it to be a proper conjugate, you need to add a number here. So that's this. So that's the C naught gate. That's the C naught gate. And finally, so if we have that's a quantum gate, right? A simple quantum gate. It's a C naught gate. So if we consider now a quantum circuit which is composed of quantum gates, right? So here let's consider a very simple quantum circuit which is composed of two C naught gates. So if we just connect them together here in the this middle line, then connect it. Okay, so we have one C naught and two C naught. So as we just said, to make the C naught this diagram a proper quantum gate, we need a green circle. So we have two C naught, so we need two green circle, right? So have two green circle. So now we want to see so what is the probability that the green test will happen on the output of the circuit if we input the green short states? So if we want to know this from this quantum gate, then we can just calculate the probability by diagrams. So as we said here, so the green short states, right, is here. So green short states is this. The green short states is this. You have a half here, right? One of a green circle. You have one of a green circle, right? So you need to. So here, for each green short state, we need to put a half, one of a circle here. So we have three inputs. So we have three these numbers. Similarly for the green test, you just flip it, right? So you need to put the number as well. Put these three numbers as well, and don't forget for this C naught we also have these two numbers. Okay, now we have a lot of we have 8 numbers. Okay, so but don't worry, it's very as we said for this number. For those numbers, you can freely move them and put them together, right? So let's put this put these halves together, put them together. Then it looks like this. Okay, now let's just look at the diagram. So let's first do to do the simplification. Let's first do the easiest thing, which is fusing the spiders. So here we have the green spiders. They are connected, so we can fuse them, right? We can fuse them here. And we have green spider here, and green spider here, and green spider here. They're all connected, and then we can fuse them, right? We can fuse them. We got this. Okay, again, for the other part of it, we don't change anything. So after the fusion of the green spiders, and then what we do is, okay, now here, as we said, because this is a green spider, right? The green spider with zero phase and one input and one output as double wire, right? So we can turn them into the plain wire. You can remove the circle. Okay, and then now we can do copy, right? We can do copy because the green can be copied by the red. This green can be copied by the red. And as we said, to do the copy, we need the help of a green circle. So we have this green circle for this to be copied, and this green circle for this to be copied. So once this copied, you get one. You will get two, right? You get two of them. So one is connected with this connect with this. The other one is here, and also this. Once this copied, one is here. They are connect. They connect with this one. And another one is connected with this, right? It's copied, one is here, one is there. It copied with, connect with this. Okay, so, and then we can do the fusion again because this connected, and this connected. You do the fusion again, it is become a double circle, right? So you have 1, 2, 3. We have three double circle. So which means we have 2 single circles. We have each one have 2 single circles. So totally here for these 3 doubled, you have 6, right? Sorry, I got a mistake here because these 2 circles there, when they do the copy, they're consumed. So there's no circle anymore. There's no circle anymore. Okay. So you have 1, 2, 3 double circles, which means 6 single circles. But here we also have single circles on the bottom. So this means, okay, this is we have 6 circles on top, divided by 6 circles on the bottom. So the total number is just 1. So that means, okay, for sure we can get the probability is 1. The green test happens will be 1. It will definitely happen. That's this. So that means, okay, we can use these diagrams with the rules and the mathematics of the probabilities to do the calculation of the probability. That's the quantum. That's the quantum gate computing. So finally, so we can look again at the quantum uncertainty. So so basically, so typically, right, when we heard about quantum uncertainty, is a very typical case is about the relation between where quantum particles are and how fast the particles moved. Was the relation between these two, right? So so now we want to use diagram to show to depict this quantum uncertainty. So how do we do that? So let's look at a simple case. So let's say that we have two sure states here. Two sure states, because as we have said, these two sure states, because if we trace them out, yeah, if you discard the output, you will get 1 for each of them. So let's say we have 2 sure states, which represent the states of a quantum particle. This represents the state as here, and this means not here. And similarly, if we can use green test, green measurements to tell us whether the quantum particle is moving or not moving. This means moving. This means not moving. So if we want to know, suppose we know now that the quantum particle is here, so which means the state is this, right? The state of the particle is this. Then we want to know whether it is moving or not moving. So we have to do the measurement. Otherwise, we won't know anything, right? So to do the measurement, that means, okay, we use the green measurements, the green spiders to do the measurement. So because we don't know, we want to see the probability, right? Because everything, once you do the measurement, the outcome, the outcome is a there is a probability, right? For the outcome. And so we need to do, that means, okay, we need to use these two measurements to measure the state, right? The given state. So they're the same here. And so let's see how do we calculate these two. These two are numbers and represent the probability of the outcome. So let's see how can we get the probability. So let's take this one is as an example. They can be calculated similarly. So how do we calculate? So because this we want to use some rules. So we sometimes mostly we for green spiders or red spiders, when we use a fusion, we put them we fuse them together. But you can also fusion rule is a equality, which means you can do unfusion, right? So if you unfuse this, if you unfuse this this green spider, so you can get this. So you can get this. You can have this two cap, the quantum cap, right? You have this. So, but why do we want this? Do the unfusion? Because we want to. As you can see, we want to apply because there's a red and green. So the typical rule we can use is the copy rule, right? So we want to copy the red by the green, and you can do the opposite way, but the same, similar. So let's say we want to copy the red by the green. So we unfuse like this. Okay, but as we said to us, because we are calculating the probability, so we need to make the diagram the diagrammatic equality strictly equal. So we need to consider scalars, the numbers. As we said, to do the copy, right? You need a so here we have two halves, but two. So let's move this half to here, So to do the copy, we need, as we mentioned before, we need a green circle, right? So then we make up this green circle with a half, as 1 over the green circle. So the whole thing is equal to 1. So it's an empty diagram, right? So we basically turn an empty diagram into this green and its inverse. Why do we do this? Why do we do this? Because we want to strictly use the copy rule. Okay, now we can have, once we have this this green number, this green circle, then we can use apply the copy rule, right? Okay, it's copied, but it's also connected, so you will get this. At the same time, you consume this number, right? Then you will get this left. Okay. Once you get this, previously they are connected, so you can use the fusion rule. So they are fused together. And so this is a circle, is a red circle, right? Double diagram. So you can write it into a two single circles, right? Two single circles. Okay, as we said before, or if you want to use the use the color change rule, just to red circle is exactly to green circle, right? The green circle. Okay, so we have three half, right? Three half, we have two, right? So finally, you will get just this cancel out with two of them, and then you will get just a single half, right? Just get a single half. So that means okay, that means okay, if we measure this state, which this particle, which is here, the state is here. So we use the not moving to measure it. Then we get the probability is half. And similarly, if we use this to measure the state, we will get this, and we do the same similarly. We will get the same probability. We will get the same probability. That means, okay, so if we know for sure that the particle is here, then we are not sure that there is a half probability that it is moving and half probability that it's not moving. So basically, you know nothing about whether it's moving or not, right? You know nothing because the probability are the same, they're all half. So here, that means by diagrammatic calculation, we find out that once we know for certain where a particle is, we know nothing about where it is going. And actually, if you do the other way, if you know for sure where it's going, you don't know where you don't know for certain where it is, right? So that's the quantum uncertainty. That means okay, we with this kind of a diagrammatic calculation, we can depict the quantum uncertainty, right? This is this is a nice thing, right? Okay, so I think that's all about the probabilities for pictures. I'm happy to answer any questions if you have.
Hello.
Hi.
Hello.
Yes, I can hear.
Yeah, please. When copying, you introduce the green circle, and the green circle is 2, right? So you introduce 2 to the numbers, and what happens to the 1/1 on green circle up there? Now,
you mean one over?
If you can move down a little.
You mean 1 over green circle, right?
Yeah, I'm talking about getting to the end of the lecture. If we can move to that side.
Sorry, which one?
Hello.
Which one?
If you can scroll down. If you can scroll down.
Scroll down.
Scroll down. Yeah, scroll down. Not here at all. Down, down, down.
Okay. Yeah.
You're scrolling up. Yes, can you scroll? Here, we have you have the green circles, and then you are copying with the red.
Yeah.
Now you introduce when you copy it, you introduce that green circle. Yeah, it was not here, but you introduce it because you are copying. You want to copy.
Yeah, I want to copy. So I introduce here.
Yes. Yeah, it means that this green circle introduces a number.
Yeah.
I think the green circle is 2. The value of green circle is 2. So it means something has been introduced. where did it come from?
Yeah, I just so as we said here, right? So I will go first. I will go here. So as we said, this one means an empty diagram, right? One, one corresponding to empty diagram. So from empty diagram, if I can make them, if I can make these numbers a one, then it's, that means it's nothing, right? I get for free.
Okay.
Yeah.
Thank you.
No worries. Any more questions? Catalina, are you there? Okay.
Okay, I think there are no questions coming.
Yes. Can we finish?
Okay, so thank you very much for joining us today for this lecture, and we hope to meet you later. So this is our last lecture for the year. Okay, so Harny, thank you very much for joining us today.
Yeah,
we
my pleasure.
appreciate your time.
Yeah, thank you for attending. Bye, everyone.